some g. Right? What we want to know about is the fraction of the time that it's going to be bound by, say, a transcription factor. Right? So then, in the simplest case, we get an input-output relationship that is just given by this, because there's just one or two copies of that DNA, so it doesn't really sequester the transcription factor that's going to be positive. Do you guys understand why this is weird, but ways to continue to be careful of? Okay. Right. And more generally, I strongly recommend that in all of these sorts of problems, it's good to just plot the things, right? So plot, for example, the fraction bound is a function of, if you vary the substrate concentration. So because this, often you think that you know what's going on, and then when you just go and sit down to draw some curve just to get your intuition, you realize you don't know where it starts, you don't know where it ends, you don't know what it does in between, and it's it's embarrassing, but it's only when you sit down and try to do something like that that you realize that it's not obvious, right? So just for example, it's useful to imagine a situation just doing a similar E and F, where if we just for the sake of argument say that F total is around this kg. Okay. Right, now what we want to do is ask, what's the fraction bound, as a function of, all right, so we're going to fix total substrate, vary the enzyme concentration. So we already know what the limit here is. Right? If you go to infinity, what should this go to? 0. Right? Right. So we know that eventually it should go to 0, and we already figured that out for kind of any finite substrate concentration. Right? Incidentally, on many of the exams, I will ask for plots of curves like this. So be aware. There's basically you want to indicate where it goes on one end, where it starts, and where is it going to start in the limit of E total going to 0? Half. Right? Then it's actually accurately described by that. Okay, so we start here at 1, and we start at a half. Okay. And it's going to have to go in between those two, right? So, but what's the kind of characteristic concentration here where it's changing a lot? Yeah, KD. KD is actually the only concentration in the problem, right? So that means that that's what sets scale. And I don't know whether KD exactly where it should be, but something in there, right? So in these sorts of situations, you want to kind of get the limit and kind of put, what is it that sets the scale? If there's a peak, where is it? All right, so I encourage you just, for a few kind of toy examples, just draw some of these things. It's a fun way to, spend a Saturday afternoon. All right. Right. Are there any questions on what we said so far? Yes. Right. Okay, the question is, what is the fraction of the enzyme that's found when E total is equal to KD, right? And yes, I think that we could figure it out, but it might actually be a little bit of math. Let me see if it's... Yeah, so I can't... I would have to... I'd have to think about it, but it's going to be around like a third or a fifth, somewhere in there. But if somebody gets bored with what I'm saying, they can do the calculation and report to us at the end of class. Okay, so right, so this what we've just done, it feels like a lot of time to spend on like two molecules binding to each other, right? But I think that it's good to just make sure that you're comfortable with the simplest kind of process before you start thinking about things that are super complicated. For example, chemical and kinetics. All right, okay, so this is not super complicated, but all right, E plus S. All right, so now it's the same thing here. where we have K forward, K reverse. It's complex, but here at some rate, K cat, the enzyme does something, right? Turns it into a product. Okay. Now, this is a model of how an enzyme works, right? It is not a perfect description of reality in any given case or in general, right? What's the most obvious possible point of concern? Yeah. No way to go back. Well, that's okay. What's the matter with that? Well, sometimes there is. Okay, yeah. Right, okay, so that's one, right. So, but I'd say the problem is in some ways more fundamental than just sometimes there is, though, right? And what's the, because, I mean, okay, right, it's true that sometimes, but sometimes lots of things happen, right? Sometimes, the enzyme binds two substrates. I don't know. I mean, so there are, on any specific case, there are many ways that this thing can fail, right? But I guess, on a fundamental, there's a more fundamental sense which is the problem. Yeah. Okay, right. So, right. So what Sam is saying is, all right, well, this K-cat is not a function of other things, and that's true, and in many cases it might, but I guess what I'm really trying to ask is, there's a real sense in which this thing is failing fundamentally kind of for any enzyme, and I just want to make sure that we're all, yeah. Dissociation of P and what? Okay, so what's the matter with it? You don't like the dissociation? Oh, I'm assuming that although I could argue, oh well, K-cat is some kind of bulk parameter that tells you about the rate of breaking some bond and dissociating, and it's a simple model. We don't want to ask too much of it. K reverse is huge. Well, I haven't told you what K reverse is, so no, it's not. I mean, it could be. I mean, so far we haven't said anything about what it is. Oh, I mean, what are the fundamental properties of an enzyme or a catalyst, for that matter? When you go home for Thanksgiving, and your grandmother asks you, honey, tell me what's a catalyst? What's that? All right, this doesn't get used up in the reaction. Okay, perfect. All right, not used up. Okay, and does this model violate that? No. Okay, so all right, so grandma's happy. Okay, so what else? Yeah. Right, so it's true that there's some enzymes you can activate, deactivate. How would you deactivate a protein enzyme if you wanted to? Yeah, you could denature it, or heat, or salt. But that's that's maybe not one of the most fundamental. Yeah. Right, so maybe there should be a rate S to P without the enzyme. Yeah, I mean, although, I'm just trying to tell you about the rate of what the enzyme is doing, So you could write a different equation, right? But I guess, in this, if I just let this model go to infinity, then what happens? You get P. And how much P is it? A lot of P? A little bit of P? Yeah, it's all P, right? And how much substrate? None, right? So if I just let this go, you have zero substrate, all product. Right?